or 10.076%.
Okay. Because I would assume that when you first start out, Nick, that the period is really close to whatever your theoretical is.
Yeah.
Okay. And then it slowly starts getting, bigger or smaller depending on which one you get towards. And again, these are not the real numbers you would use for your
Yeah.
lab. But
So what about like none of our period stays relatively the same? Like it goes
so
up.
after through 90 degrees, you're still within 10%.
Oh yeah, way within 10%.
Then you just write still within 10%.
All right.
Yep, I probably should adjust that.
Yeah, it's like 10% for my periods. 1.8865 is the upper limit. 1.5435 is the lower limit. I don't go below 1.715 or go above 1.8.
All right.
I'm well within it.
So, assuming that the pendulum is simple, based upon the angle, it seems like we really don't have to worry about that.
So then like the next one says should the two answers above be close to the same? But if you're talking about time, you're talking about an angle.
Right. So what do you think?
I don't think it necessarily is the same.
No, they're two different units.
What was the question for this? You said two different units. Be careful about the wording there. Because the question asks, at what angle are you off by 10%?
Yeah, the first one, at what angle is a small approximation off by 10%? More specifically, when is the sine of the angle off by 10%? And the other one's determine the angle at which the period is 10% off of the theoretical value.
That was a keyword that might want to grasp. So that's. Okay, so I'm asking for an angle in each case. So
Okay.
when you said different units, be careful about that, because I am asking for an
okay.
angle. But it, apparently, not an issue. Not an issue here, is an issue here.
Mm-hmm.
Yeah, that really is not less than a 0.3 second difference.
Mm-hmm. Let's stay for this one.
Yeah, when I emailed you about 3 and 4, your email helped me on 4 because I'm not that great at abstract thinking, like the sign thing. I just didn't get it because until you showed me.
Okay.
I think, but I'm pretty sure I got number 4 right.
All right.
Because shouldn't it, it's dependent on what you got for the theoretical value, isn't it?
Correct.
So, it could be different from question 3, the angle.
Yeah, and apparently it is.
Yeah, that's.
All right. Any other questions on the lab? Come on. All right, and you had a question on the master set?
Yes, on question 3 on master circle.
Near surface of the earth, okay, and it's sprung horizontally. The spring is hung horizontally. Over a horizontal run, so it's hung vertically.
Yeah.
Spring hangs, and it gives you the length, we add a mass to it, it's lowered until the spring hangs that distance, the spring constant. So basically that mass causes it to drop from 0.953 to 1.576 meters.
What?
So I give you,
On,
am I looking at the wrong problem? Problem 3.
no, the spring is in place, I mean, this part.
Okay.
Yeah.
All right, so once you have the spring constant, then it's placed on a horizontal frictionless surface. One end is fixed, the other end has a mass attached to it. So that's, should be similar to things we've done in class. At least that piece of it. And there's a mass attached to it. Then it's displaced a certain distance from equilibrium. So we pull it out or push it in. Do I say pulled or pushed?
The mass is displaced.
Okay.
Distance. 5.4 meters.
All right, I'll just round off, 6 meters. We'll just say K is 20 newtons per meter, this mass is 4 kilograms. Obviously not the same numbers you have there, but. So I pulled out 6 meters and I assume let go.
And there's the total mechanical energy, the maximum speed, the maximum acceleration, and a different displacement.
All right, so,
What I had trouble with was the maximum acceleration, because I was getting like really high acceleration, like super high, like almost speed of sound level.
well, they're 2 different scales, so.
Right, I know it's acceleration, it's not meters per second, it's not the actual velocity of the object, but it just seemed wrong to me, and I couldn't.
All right, so what was the spring constant that you had?
It was 339, or 336.629 newtons meters.
All right, 330 something, so I'll just say 300. Just give the ballpark numbers here. This mass was 5 point something.
Yeah, 5.87.
So this is a really high spring constant. It takes 300 newtons to stretch it a meter. My weight is about 900 newtons at this point. So a third of my body weight is required to stretch this thing a meter.
Right.
I'm gonna stretch it out 6 meters, so I got a lot of force acting on it. Or 5 meters in that case, it's still a lot of force acting on it. So when you let go, there is a lot of force. So the acceleration is force divided by mass. The force acting on it at the extreme, because that's when you're gonna get the biggest acceleration, because you have the biggest force when you have the biggest stretch, would be K delta X divided by M. So that would be 300 times 6 divided by 5. So that would put it at 360 newtons. Oh, sorry, not newtons.
Meters per second squared.
Yeah. Yeah, so that's 36 Gs.
Okay, so.
A human would black out.
So I was correct on the maximum acceleration, because
Yeah.
it was like 314.
Because I put a rather large mass on it initially when it's in the vertical position, and it didn't, I don't think it stretched the meter if I recall the numbers.
It stretched, 0.683, I think.
Yeah, that's a lot of mass to stretch it that, not much. So, yeah, they're just ridiculous numbers.
I was so lost, cause I was like, how is it? Cause the actual velocity isn't that much. I mean, it's a lot, but it's not like 300.
Yeah, I guess the period is small.
I don't know, we didn't do the period wasn't long.
Okay.
And, I also had a problem with number 4, the equations to describe the position,
Yep.
or the velocity or acceleration. I got those, but I
Okay.
don't, I had trouble with the next set of questions where it says, what times is the mass 0.5 meters above the equilibrium?
Okay.
I didn't really get that, because I assumed the amplitude was 0.85 meters, and I didn't know what, if I had to add the 0.5 meters to that.
Alright, so it's hanging vertically, like,
Mm-hmm.
alright, so it's hanging vertically, it's pulled down or pushed up, whichever one it was, and let go. So how far it was pulled down, initially, before it was let go, is the amplitude. So it's gonna oscillate between there and here.
Mm-hmm.
And the question I asked was, at what time is it, what, 0.5 meters above?
Yeah, so what I did was I just added that so it was 1.35 meters in total.
Yeah, no, wrong approach. Alright, so if my position is, and again, making up numbers here, let's say this is 1.5 meters stretched initially. So I got 1.5 meters times the cosine of whatever omega is.
Yeah.
So what was your omega?
3.395 radians per second.
Alright, so I'll just make it 4 radians per second. Radians per second times time. And then there's no phase shift because it starts at the maximum amount like a cosine does. Now, I've set it up here when time is 0, this term here is 1. Cosine of 0 is 1. Times 1.5 meters, so initially I'm on the positive side.
Mm-hmm.
By this equation, if I want to start out on the negative side, that'd be a negative number. Is that the question where I asked what's the direction, which way is positive, which way is negative?
Yeah.
Okay. And you said which way was positive, which way was negative?
I just said it could be either one depending on where you determine the position.
Yeah, I was asking you to determine which you were gonna do.
Oh,
Well, I answered it the same way.
okay.
Yeah, because that will affect how I mark the rest of your answers. What did, for the position, did you have this as a positive?
Yes.
Okay, so you made down, and I initially stretched it down, right?
Yeah.
Okay, so you made down positive.
Yeah.
This is saying, if I pulled it down and let go.
0.85 is positive, yes.
Yeah, so, alright, so down is positive. It's a one-dimensional problem, so I don't need a unit vector here. I don't need I hat or j hat. I can get away with just plus or minus.
Then you said explain.
Yeah. So, the position here is 0. By having this as 1.5, if this initial position were not 0, you'd have to have another thing out here. There'd be a plus something. But this establishes that I start out 1.5 meters, given this example, 1.5 meters from 0, and then it goes to 0, then it goes to negative 1.5 meters, and then back to 0, then back to negative 1.5, then back to positive 1.5. But basically,
So it doesn't go back down to just 0.85.
it doesn't go back down to point.
So the question was, if it's initially displaced downward 0.85 meters,
Okay.
how long would it take for it to get to 0.5?
5, right, okay.
Above the equilibrium.
So I'm doing 1.5 instead of 0.85.
Yeah.
So the time it takes is, I'm trying to figure out the time in which the position is here, a half meter above where I started.
So the total.
Displacement is looking at where you are relative to 0.
Okay.
So that's 0 right there. Initially, your displacement, if down is positive, displacement is positive, whatever that is. I want to know at what time is this equal to negative 0.5? Because if down is positive, this is positive down here, it's negative when I'm above it.
Okay.
So you're
That
basically,
Makes more
like
sense.
minus that negative to be flipped.
if you said up was positive, then this would be negative here, and this would be positive here.
Okay.
These will be opposite signs.
Gotcha.
And so therefore, in this, my example, we have cosine of 4t is equal to negative 0.3 repeating, divided by 1.5. So the cosine of some angle is equal to negative 0.3. So that angle, well, I have to get rid of the cosine somehow, and I do that with inverse trig function, so that's an arc cosine. That'll get you some value on your calculator, or probably most of your calculators, it'll be cosine with a -1 there.
Wouldn't there be a 2π there?
Where?
Oh, sorry, wrong word.
Okay. And then once you have that value, divide by 4 to find the time. That's the time at which it's at that going up. Then it hits the other point, and it hits that point 0.5 above the starting above equilibrium as it's going back down.
And we're still in radians right now.
Yeah.
Okay.
Yeah, it is assumed that we are dealing with whatever we get for the arc cosine. Yeah, we would get radians. We would need to be in radians. Unless you converted your angular frequency into degrees per second. Chances I have one of those here, so I don't have to keep asking what it says. Wrong class? Okay, I don't. I guess, Nick, you have your copy back there, right? You just grabbed it.
Oh, which one? Yeah, the
The
master
master
set?
set?
Yeah.
Yeah, could I, anything about this?
Yeah.
Please, thank you. All right, so problem takes place near surface of Earth. This gives us a, that, we know the value of G if we need it. All right, so initially, so I gave an initial position. Then I put a huge mass on it, gave a final position. Then asked for the spring constant. And then I put it horizontally. Oh wait, am I on the wrong question? No, you're on problem number 4. Sorry, that's 3. So I gave the period, and it was pulled downward, so I gave how far it was displaced from 0. Well, why don't I just work through a problem with?
Do you need the mass?
Oh, no. Yeah, I'm not sure your mommy.
Yes, if I needed the math,
The mass of the,
I'm gonna make numbers up. There it is. All right, so I gave the period, so let's make the period 4 seconds. The mass, we'll make 3 kilograms. And the initial displacement, so on a horizontal, I believe. So it's pulled, or is this one hanging? Is it hanging vertically or horizontally?
suspended.
Suspended, all right. So the mass on it, it's some position there, then I pulled it down, I think I gave how far I pulled it down. So we'll just make that 1 meter. And then let go. Now it's gonna oscillate back and forth. So the first three questions, I think the information was given to you, that's why I put a little gift icon there. Because I think one of the questions I asked was, what was the period,
Yep.
which is given in the problem?
What's the amplitude and displacement, positive or negative?
Yeah, and displacement positive or negative, I don't care which one, but it does affect the rest of your answers. So, you said up was positive, Nick, is that right?
Yes.
And John, you said down was positive,
Yeah.
ultimately. Adam, not there
Down
yet?
is positive.
Pardon?
Down is positive.
Down positive, okay.
No, when you say explain, it is because I say it is an
Yeah.
acceptable answer?
That's perfectly fine. So down positive, the amplitude is how far I stretch it from equilibrium. So that, is it 0.85 meters in the problem, or whatever that number was? All right, I need to know the angular frequency. I know that the period is 2 pi times the square root of m over k. There are shorter ways of doing it, but it's the way I'm doing it right now. So this is 2 pi times the square root of 3 over k is equal to 4. So you solve for k to get the spring constant. Yeah, I'm throwing an extra step in here, but this is just the way my mind's working right now. So 4 divided by 2 pi is equal to the square root of 3 over k. Square both sides to get rid of the radical because I'm trying to get to the k. So that becomes 4 over pi squared is equal to 3 over k. And so k would be 3 pi squared over 4, which is roughly 7.5 newtons per meter. It's a quick, pi squared is roughly equal to 10. So once I have the value of k, I know that omega is the square root of k over m. So that's the square root of roughly 7.5 divided by 3. I don't have to worry about units because I'm in SI units. I got kilograms, I got newtons, I got meters. I'm dealing with all the nice units. So my units for omega are going to be the nice ones, radians per second. And this is roughly, again, crude approximation, about 1.5 radians per second-ish.